But anyway, that pretty much ends my rant against downlights. But I do want to show one last slide on lighting. On the left here we see an incandescent bulb, such as the ones that were famously outlawed by Malcolm Turnbull in this country not too long ago, versus an LED bulb, which again is putting out a similar amount of light. We can see on the incandescent 101 degrees, and on the LED there is a little bit of a hot spot at the base of the bulb, reading 42, but generally the bulb itself is relatively cool to the touch and not much warmer than the rest of the room. So that's the technology of LEDs that is available these days. I think that was about a 60-watt bulb there versus a 5-watt LED, giving a similar amount of light. All right, get off of lighting for a moment. Let's talk more about insulation, ceilings and walls. Now, probably this is the main advantage of the camera, the way that it can see right through the ceilings here. And this is what I would say from my experience is not the worst insulation job I'd ever seen. It could be better. You can see a cold spot around the downlight, as you always expect. And the insulation doesn't go quite completely out to the wall or to the eaves. And this is because for an external wall like that, your roof is coming down like that, and the insulators don't often want to stretch and get themselves right out to the very edge of the attic space. And so they'll leave a gap like that. This is a common fault, but still, like I said, from my experience, this is probably an above average installation. And you can compare that with this image. This was taken on a hot December morning at 11:30 a.m., and parts of this hallway ceiling are already reading 29 degrees versus the insulated parts were as cool as 24. I take these bottles into work, and somebody said, "That looks like a beer bottle." I said, "It is." But doesn't mean you have to have beer in it. Anyway. So what we have, we've got a lack of insulation, 29 degrees, 24 degrees. So this is, like I said, 11:30 in the morning, and that temperature is just going to keep going up throughout the day. And so the occupants of this house will probably go to the movies, go to the beach, or turn on the air conditioner. This homeowner knew they had some insulation, but they thought they had more than this. What actually went on in this attic space, I have no idea. Possibly a renovation either added or took away some insulation. But here now, we're still in the same house, and we go into their kitchen. And it may be that the hallway was the coolest part of the house. This kitchen is insulation-free and running at 31 degrees at 11:30 in the morning. You can see the ceiling beams themselves, and they're actually providing a little bit of insulation. But again, let's focus on the bright side. This problem is easily and cheaply fixed for a few $100s, although the homeowner would want to wait till a cooler day before they took on the job. And depending on how much they run this air conditioner here, can you imagine how much money they're going to save or how much more comfortable their home is going to be when they put in some insulation, or if they do it properly, put in the whole R6.0. Then they wouldn't have to worry about heat coming in from their ceiling anymore. And can you imagine the reduced drain on our gas and electricity networks if every home in Australia were properly insulated? Indeed, the so-called failed government Pink Bat scheme was actually a huge success because it installed insulation in 1.2 million Australian homes. And this did have a noticeable impact, reducing gas and electricity demand on the system. But there still remain about 1 million homes in Australia that aren't insulated, and millions more where the integrity of the insulation has been compromised by downlights. Whoops, I talked about downlights again. Another ceiling, there's another downlight, okay. Another ceiling, and here a combination of downlight and some other fun and games up in the attic space. Now, of course, what the assessor wants to see is complete uniformity of temperatures over the walls and the ceiling, basically the same temperature everywhere, like this. And this goal can be achieved in Australia. I assessed one home in Brighton. Where's Ian? Where'd Ian go? Is he still there? I assessed one home in Brighton, and we already knew that this home was very energy efficient. Try as we might, we could not find a single feature in the home that was worth taking a picture of. That home is so well insulated that Ian and his wife, who designed it and lived there, they can heat their home simply by cooking dinner or by watching television. They weren't disappointed that I wasn't able to take a single photograph. In fact, they were pretty happy to know that things were working out just the way they'd planned. Still looking at ceilings, If you do get up there and insulate your ceiling, on the way down, don't forget to do the access door. Now let's look at some walls. The thermal imaging assessor will pretty much find the same thing in the walls as in the ceilings. No insulation, incomplete insulation, fantastic insulation. Here the insulation stops partway up this wall. Now what happened there, I don't know. Maybe the builder ran out of bats, or it was lunchtime. But I would very much recommend to any homeowner doing a renovation or a new construction that they tell the builder they want the job done properly. And to remind the builder, you will be on site to inspect before the plaster goes up. Unlike attic spaces, if you don't get the walls right to begin with, it's very costly to fix them afterwards. My wife and I were having a renovation done, and just before the plaster was going up, around the edges of the windows, I could look through and see the kids walking to school. So that wasn't good enough. Since I come from North America originally, I know that if you did such a poor job of insulating there, your building cavities would fill with ice, water, and snow in the winter, and your whole house would fall apart in about 3 years. The problem in most Australian capital cities is that we generally have not had the sort of climate that will kill us or will knock down our house in about 3 years. The cost of energy in Australia has been perceived as being cheap, but partly that's because we pay with our energy little by little every 2 or 3 months, while home upgrades have been perceived as being very expensive, but partly that's because you pay for that all up front. And remember the good old days, we were all tougher and we didn't really care as much. We would just sweat or shiver until the weather changed. And lastly, we weren't as aware of the climate impacts of squandering energy. But no more, so now it is time that we upgrade our homes. More wall insulation in Melbourne, and this is a real mess. This homeowner asked me to check out his young son's bedroom because it was a bit hot. This image was taken in the morning on what was to be a hot day. The inside wall is acting as a radiant heater at 45 degrees at 11:30 in the morning. It will be many hours, if not days, or maybe even months, before anyone can stand to go into that bedroom. Or they might just turn on the air conditioner. But who in their right mind would run a 45-degree radiant heater next side by side with an air conditioner? But that's what happens. This homeowner will be up for some expense to fix this properly. And I don't know if this is shoddy building practice or if just the building standards that we had in the 1970s and 1980s. But it does raise the question, why have rooms that for large parts of the year we have to abandon? Homeowners have a lot of capital tied up in real estate. Seriously, one solution might be to move to a smaller, energy-efficient house. All right, a little something different now. Spot the possum. Looks like some of you found it. I could hear it, but I couldn't see it until I got the camera, and there it was. There it is. Now, what's going on here? Who's at fault? It must be this nasty native vermin. But actually, no. What has happened is following a minor renovation, the builder has failed to put insulation into the wall space. Right? And a builder before that didn't properly seal the metal roof to prevent possum ingress. So this possum has found a nice place to sleep during the day. Although since this is a western wall, I'm not sure if he intends to stay there all summer. The interior upstairs bedroom wall is reading 41 degrees at 6 o'clock on a November night. Not the most comfortable bedroom, but in fact I can report that this possum didn't stay there all summer, because this is my house. And this bedroom is now my office. I removed the weatherboards, chased out the possum, and installed some insulation. I had to, otherwise that room would not have been livable enough for me to prepare this presentation. Doors and windows, keeping the heat outside. We've seen a bit about how hot it can get inside, but let's step outside for a moment. Here we see a wall reading 51 degrees in the afternoon. This is a 30-degree temperature difference between that wall outside and the 20 degrees that we'd like to have inside. So we really want to keep that heat outside and not let it get inside. But it gets hotter than this. Here's a hot deck right outside a kitchen door. That deck is acting like a radiant heater at 56 degrees, reflecting heat into the kitchen. But it gets hotter. A different deck, a hotter deck, and inside the kitchen floor area, it reads 67 degrees. This would be a wonderful heater if it weren't a 35-degree summer day. But it gets hotter than that. 81 degrees. What's this telling us? It's telling us that Melbourne can get hot. And so we need to employ strategies to keep that heat outside. Those strategies might involve exterior eaves, awnings, window tinting, reflective films, low emissivity films, double glazed windows with tint and film treatments, deciduous trees and other vegetation, and as the last resort, interior blinds, shades, drapes, and curtains. And I say that the interior blinds are a last resort because you really want to keep that heat outside. Here's an example, my own lounge room. North-facing box bay windows, double glazed, of course, with some tint and some expensive double-layer duet blinds inside. But not good enough. The inside of these very large blinds is radiating heat at 33 degrees, making that lounge room unlivable on a hot day. So the solution? External awnings. This was a bit tricky for the box bay window, but this $120 retractable shade cloth item seems to do the trick while not looking too bad. This is a west-facing bedroom window. I haven't fixed the north-facing windows yet, but I'll do that just as soon as I finish assessing everybody else's home in Bayside. Here's another west-facing window upstairs where this blind is. So the blind's drawn in the afternoon, but still this blind is acting as a radiator to the inside at up to 42 degrees. The blind over here looks like it could be cool, but it's actually hot as heck. Now you can also see through the blind that I've stuck some sections of this perforated aluminum foil on that window. And it does make a difference. Down here we can see that without it, it's up at 42 degrees, and the aluminum might knock it down to about 39. But still not good enough. So the solution for this window, cheap and nasty, I got a piece of cardboard, take the aluminum foil on one side, and just put it up there against the window, and actually it doesn't read much hotter now than the walls, the insulated walls next to it. So that was a cheap solution. But sometimes folks don't like the way that those cheap solutions look. Here's a photo of that perforated aluminum foil on our garage for west-facing windows. It certainly does reduce the heat, and it's easy to apply. But if you install it in an obvious place, maybe it's not that attractive. My son lives above the garage. He thinks it's good because it keeps his room cool and it makes it look like a meth lab. One thing about doors and windows, and that's the thermal break. But you may ask, what's a thermal break? Here's an image of some double-glazed bifold doors, but the owner wanted to see what they look like through the camera because he knew the aluminum frames were not thermally broken. These aluminum frames. What does that mean? Well, it means that the frames are simply aluminum the whole way through. And aluminum is about the best conductor of heat and cold. So you spend a lot of money on double-glazed windows, but you're using aluminum for the frames. And so that's letting a lot of heat in. So sure enough, there's probably more heat coming through those door frames than the owner would prefer. Ways around this? Well, when purchasing new double glaze, look for doors and windows that have plastic PVC frames or are a combination of aluminum and wood that stops the thermal transfer. Or you can get them with the thermal break, which is a bit of plastic in between the aluminum, which we saw in the previous slide. While we are still on the topic of thermal heat, let's just look at how hot some living spaces can get. This ceiling space in this kitchen is reading 46 degrees at lunchtime. The owner there is green as, but as often happens, this homeowner just said, oh, well, I'll just suffer. It's only hot on a few days. But one thing he didn't consider in saying that is that on these hot days in his kitchen, his fridge is also suffering and using more energy than it might if the room were kept cooler. And so he's decided to have a look at these films and tints that you can put on the glass. Skylights are good green things to have, right? They let in natural light and it saves using a light bulb. However, this skylight space here is reading 51 degrees. But there are things that can be done about this. You can insulate around the tunnel. You go in the attic space and actually insulate the tunnel up to the skylight. Quite often that's forgotten. You can get double glazed skylights and skylights with certain films and tinting, but then you're trading off the amount of light that's coming in versus the heat. And also, sometimes these skylight blinds can be fitted. Sometimes we do things with the best of intentions, but then they backfire on us. A number of years ago, the Port Phillip Eco Center down in St. Kilda wanted to showcase some newer type of ceiling insulation, and it's shown here, keeping out the summer heat. But to showcase this insulation, the renovators created a cathedral ceiling. But what they might not have thought about was that in creating a cathedral ceiling, they also created two new walls, which were uninsulated. And so the ceiling may be doing a good job, but these walls, these uninsulated walls, are letting in a lot of heat. And this is in a space that the Port Phillip Eco Center uses for public meetings, so they would like this room to remain cool. Here's the outside of the other uninsulated wall there, and it's reading 42 degrees, so that's going straight into the meeting room. But fortunately, this is not too hard to fix. The first interior wall can be accessed, and so they can put some insulation on there. And for this outside wall, it looks like it might be about time to replace the weatherboards anyway, so when they're doing that job, they could put in some insulation. So we fight to keep the heat from entering the home. However, we have within our homes stacks of electronic games, gadgets, computers, TVs, phones, many of them using standby electricity. So what does the thermal camera tell us about those? Well, if a device is using electricity, most of that electricity, maybe even 99%, ends up as heat, and it's in your house. Here's a bedside clock radio. I used to have one of those, and they use only 35 watts. But that is 35 watts of heat that I didn't actually need next to my head on a hot night. So I unplugged that clock radio, and these days, if I need to wake up, I use a mobile phone as my alarm clock. Here's some more devices using electricity, sometimes even when we think they're turned off, generating heat the whole time. Sometimes when I see all this standby power being consumed, it's almost if we've gone on holiday and left the planet dialed into self-destruct. With all this talk about the heat, I'm getting a bit hot, so maybe it'd be a good idea to turn on a fan. But maybe not. Maybe not this one. One afternoon I had my office largely closed off because it was just so hot outside. So I had the windows closed and I decided to run this ceiling fan. But a little while later, I put the camera on it and I found out it was generating heat at 50 degrees. So now I'm not such a fan of running big ceiling fans in the middle of the day. But there is an alternative, and of course that's a small room fan. These are much better. They can be aimed to blow the air directly onto my body where I need it, and this uses only 50 watts, whereas the ceiling fan might be using 200. The thermal imaging camera can only find a temperature of about 40 degrees on this fan, and there's far less electrically generated heat being pumped into the room. So are ceiling fans of any use at all? Well, I think ceiling fans can be used, say, after the cool change comes through. You can turn them on and that can blow the cool air around a lot and try to cool your house down more effectively with a fan. But I'm still not cooled off, so I'm thinking maybe it's time for a beer. So I'll just go out to the second fridge. Oh goodness, here's the fridge in the garage. But let me tell you, I'm really now very hot because the roller door is acting as a radiant heater in this here garage at 43 degrees at 11:40 in the morning. And I wonder how hard that second fridge here is working. The answer begins with an F, flat out. If this fridge were an Esky, and this family were out camping, they wouldn't put the Esky in the 43-degree sun if they could possibly avoid. I didn't do any detailed calculations or other measurements, but I did tell the homeowner that this second fridge would be costing them hundreds. Often I have people ask me about solar panels, but they're worried about the payback of solar panels. Will it pay back in 2 years, 5 years, or 10? I say, by all means, invest in the solar panels. But if you want a payback of, say, 10 seconds, go out and unplug your second fridge. And other unnecessary energy burners that you have around your home. Here's another second fridge. This time it's not in the garage, it's in the kitchen. Now usually the second fridge is older and less efficient than your first fridge. So therefore it runs longer and hotter, or both. This second fridge is putting 44-degree heat into the living space of this home on a hot day. Perhaps the homeowner should move this fridge into the garage. Just kidding. More seriously, maybe he can find a way of living without it. Now some people think I have something against beer fridges, especially those fridges that run all year long only to cool 2 bottles of champagne. But it's simply not true. Beer fridges can be great. They just have to be properly designed, like this one. This is the sort we had in America when I lived there. And by the way, in America, you can see they're so proud of their wall insulation that they even leave it on display for everyone to see. Just before we move on to some more winter fun, I'd like to have everybody just stand up and stretch a little bit. Shake it around. Create some air. Because I'm still hot. All right. So that was to signal a change of seasons. So we're going to go from summer, now we'll go into winter and look at thermal images, and they'll take on more of a blue-purple sort of character, as you'll see. First, we have to go back up to the ceiling again, and what do we find? Downlights. Poor insulation, this time not heat coming in, rather cold coming in, or heat escaping, however you want to look at it. Insulated, this ceiling is 20 degrees, uninsulated, it's only 15. So that is a huge difference to this occupant on a cold night. And here we see more of the same thing caused by a downlight installation. Now down to the walls. We have these wacky things in Australia. I call them spider vents. Now I'm not sure why we have them. I never saw these when I was living in America or in Europe or when I visited Japan.
They were required by building standards here in the 1960s. My house was in
Okay. See, I was thinking. See, I was thinking they just represented the Australian love of fresh air. So in the homes that I visit these days where we have these things, I tell folks to plug these up. Some of them, of course, you can see daylight coming right through the vents. That's how wide open they are. Unless, of course, from the safety perspective, as we were mentioning here, if you have an unflued gas heater, or if you're concerned that you may have toxic gases like carbon monoxide building up in your home, then you'd want to leave the vents open. But like I say, new Australian homes don't have these things. Not many homes have unflued gas heaters. And so plug them up. Because when I plugged them up in our house, I climbed up the ladder, and it was a cold day. The wind was blowing in off Port Phillip Bay. And by the time I got up there and the wind was coming through those vents, it about blew me off the ladder. So I can't believe it took me like 10 years to do that. I've read that the average Australian home has a sum total of air gaps representing a window 1.5 meters square that is continuously open. So those are the air gaps in your average Australian home. It is time to close that window. Here's an image of a never-used fireplace. Now, how much heat is going up that chimney? I don't know, but the camera records a low temperature here of 12 degrees. A solution here, and I think the government has been giving these things away for free, are air-blocking chimney balloons. And as you can see here, if you don't ever use your fireplace, you only have to take it out once a year on Christmas Eve. Gaps under doors. Here we are measuring a minimum of 11 degrees. I think that was 2 or 3 degrees warmer than it was outside. So this carpet snake's not really doing the job. And a better solution would be a proper door seal. I'm only joking a little bit when I say that thermally, many Australian homes are not much better than glorified tents. And in fact, I've been in more comfortable tents. Here's some windows in winter. Ideally, of course, you'd want to have double glazed and also heavy drapes or blinds, but here the camera is reading just above 10 degrees on the inside surface of this window. So inside the house, 10 degrees. Now we all know it's not very pleasant to sit or work close to such a window, so we move away from such windows. So poor thermal performance has a way of shrinking the useful living space we have in our homes. Now let's go outside and look at windows from outside the home. So now we're outside, a different house, a different day. The outside walls are reading about 9 degrees on this July day, and the window's reading 14. So that helps us to envision the heat that's escaping, being radiated out through that window, when we've paid good money to generate the heat in the first place. A single pane of glass is a horrible heat insulator. So what to do? What if you don't have the money or inclination to run out and replace all your windows with double glazed? Here's an option. This commercial product, a relatively low-cost plastic film, can be placed over the window, forming a cheap sort of double glazing. Does it work? Well, this image, taken from outside a home, demonstrates the effectiveness of this film. The thin piece of plastic wrap has been installed inside the house over the window frame here on the left, whereas there is none of it on the right. And you can see the temperature difference. So this photo is taken from outside, and with the film, we only can record 10 degrees, whereas without the film, it's 15. Heat pouring out through that window. So they actually do some good. And there's a lot of other cheaper and more shortcut ways to deal with double glazing rather than a full window replacement.
Would that work for heat as well?
We'll come back to the questions at the end there. And that way we get the whole group involved with answering questions I probably don't know the answers to. So this is a dramatic improvement. But while we're out here in the cold, the water heater. This is an image of a water heater from outside the house. And here's the pressure relief valve, glowing white hot at over 40 degrees when it's only about 9 degrees outside. So what can be done about this energy and money loss? Well, you can buy these little insulated boxes that are trade named the Valve Cozy to fit over those valves. And on this slide, you can also see that other fittings have been uninsulated. So those should be insulated as well. You can see why this might be a good idea. Heat from the water tank is leaking out into the winter night, night after night after night at 40 degrees. All right. I only have 2 or 3 more topics to cover, but now we're going to go to the land down under, where spiders fear to tread. Actually, we thought it might be a good idea to take the camera down under the floorboards and see what's happening down there. And we were going to go look at ducted gas heating. So this is ducted gas, the ducts for the gas heating system that you can see there. What did we find? Well, here are some ducts. Of course, no insulation is perfect, and so they light up a bit, meaning that some heat is being lost from the ducts to the outside environment. But actually, there's nothing there that was unexpected. And similar in this slide, really nothing that was unexpected. Here's where the duct goes up into the room, and really nothing there that was terribly surprising. But what's this? We didn't actually need a thermal imaging camera to see that this duct has unfortunately been crushed. So there would not be a lot of useful air that's able to get down that duct to the room that it's meant to be heating. And this crushing event has resulted in some duct leakage as well, evidenced by the orange colors that you see, reading up to 34 degrees. Hotter than the background temperature, which was about 15 degrees. But then we found absolute disaster. Another crushed duct, and one that was completely parted, separated, a joint that was not done up. So a full blast of expensive heated air pours out into the crawl space, doing nothing to heat the house. All unbeknownst to the homeowner, who would have had only one option to try and keep himself warm on a winter day, which is to turn up the thermostat and keep the heater running longer. Fortunately, the bright side, now that this problem's been identified, it's actually pretty easy to fix that, and he'll see some dramatic improvement in his gas bill. But how long had it been like this? Well, the homeowner's 30-year-old son was there on the day, and he reckons that he might have caused the damage when he was crawling around underneath the floor when he was a child in 1993. Horrifying. So think that you can't see can't hurt you, not true, and think that things that were installed 30 years ago are still ticking over nicely, I wouldn't trust your luck. One last thing about ducted heating, and here are some images from a different house at a different time, because in the house I just talked about, you could hardly get any heat coming out of the ducts, out of the registers. Often in our homes, we unfortunately arrange that the heat coming out of the gas heating registers flows onto cool windows, behind curtains, under beds, under desks, into rooms that we're not using, and that we don't or can't zone off, and everywhere else, rather than where they might do some good. This is another one of the inefficiencies of ducted gas heating in Australia. In Bayside's buildings plan, ducted gas heating is not recommended because of these and many other shortcomings. What the Bayside buildings plan does recommend is that your home and even your hot water can be heated with a heat pump. For those of you who attended Trent Hawkins' presentation on the buildings plan back in September, you would have heard an explanation of how heat pumps work. But I'm going to have another go explaining this technology, aided by my last thermal image. Why are heat pumps so hard to explain to people? They're not magic, but they are counterintuitive. Whereas heating a house with gas is pretty easy to explain. It's similar to what humans have been doing for 1,000,000 years. With gas, you take something that burns and you burn it. That's pretty easy to understand. Something like this paper, just burn it. But it's not magic. That's easy for folks to understand. With a heat pump, nothing burns. Nothing even gets that hot. But heat pumps aren't magic. They're just difficult to explain. But let's try. Okay, a heat pump is a device that moves heat, or pumps it, from one place to another. Maybe you don't want the heat here, you want to pump it there. Or maybe you want the heat there, so you pump it there. A heat pump is not intended to generate heat, nor does it generate cold. Rather, it takes heat from one place and puts it somewhere else. In 1834, Jacob Perkins built the first working heat pump. He needed something to keep his beer cold because he'd run out of ice. So he built a vapor compression refrigeration system to take the heat out of his beer and put it somewhere else, in the outside air. His device we now call a refrigerator, but it was the first working heat pump. So a heat pump is a fridge, and your fridge is a heat pump. Your fridge takes heat from your beer, which may only be about 4 degrees, and yet your fridge somehow, not magic, is able to move that heat away from the beer and reject it into your kitchen, even though your kitchen might be 27 degrees. It uses the technology of Jacob Perkins' vapor recompression cycle to pump the heat from your beer uphill, in a sense, so that it can be transferred somewhere else, away from the beer. As we see here, your air conditioner is also a heat pump. On a summer day, it takes heat from your lounge room, perhaps at 27 degrees, and pumps it outside, even though it might be 42 degrees outside. But you can also run your air conditioner heat pump backwards as a heater. And this is where the word reverse cycle comes into play. Some folks who own these things think, well, yeah, I could use that as a heater, but there's just some old, inefficient radiant heater up in that box, isn't there? Well, no. When you run your reverse cycle air conditioner backwards as a heater, you can heat your home at a cost of about 1/4 of what you might pay to generate heat with an inefficient electric radiant heater. And this is because the heat pump is not intended to generate heat. Rather, it captures free heat that is available in the outside air and pumps it uphill into your house. But how does it do that, especially if on a cold winter's night it is only 5 degrees outside? Well, maybe this thermal image helps to show where that free ambient heat comes from. That free heat comes from the outside air. On the cold August night, when this image was taken, the outside air is at a temperature of only 5 degrees. But thanks to the refrigeration cycle demonstrated by Jacob Perkins in 1834, the heat exchanger inside here is reading minus 1.8, inside this black hole here, so to speak. That's operating at minus 1.8 degrees, which is cooler than the surrounding air. So free energy or heat from the surrounding air, heat that actually came from the sun originally. So it's fair to call this a form of solar energy, and some people do. This free energy from the sun, which heats up the air, well, now that air can flow into the heat exchanger, heat that up the heat pump in that black hole, and then that gets pumped up to, say, 30 degrees to heat your home very efficiently on a cold winter's night. So you don't pay a lot to generate heat with a heat pump. You pay less simply to shift heat. And the BZE recommended heat pump systems have no air ducts. The heat is transferred from the outside unit into your house using pipes filled with the refrigerant liquid. So there are no air duct losses underneath your floorboards or anywhere else. BZE researchers compared the cost of operating a reverse cycle air conditioner as a heater versus operating ducted gas heating. And there's a good chance, should you have the choice right now in your house, because you have both, there's a good chance that using your heat pump is already the cheapest way to heat your home, instead of turning on the gas. The exact economics depend on the efficiency of your heat pump, the efficiency of your gas heater, including when was the last time you had it serviced. Mine's been there for 25 years. We've never had it serviced. And what's the condition of your gas heating ducts, and whether or not you're able to zone off areas of your room, areas of your home when you're not using either form of heating, and other factors. But the point is, Australian homeowners should become aware that they don't have to use fossil gas anymore. And using fossil gas might not even be the cheapest thing to do anyway. Thanks to advances in heat pump efficiency, Australian homeowners now have the option to economically disconnect themselves from the fossil gas grid and to operate their homes 100% solely on electricity. And if green power is purchased, and if part of your electricity is supplied by your solar panels, your home can now run on 100% renewable energy. The end result, a zero emissions home. And I know that one person in the audience has a zero emissions home. Richard at the back, I don't know if there's any others that have removed the gas meter. It can be done. Here's my last slide. BZE's building plan research has found that your average Australian home are glorified tents. They can be retrofitted to consume less than half of the energy that they currently use. And I hope the images I presented tonight show that in some cases just how easy those first steps can be. And it is happening already. This chart from the Australian Energy Market Operator, or AEMO, shows the actual electricity demand in Eastern Australia falling over each of the last 3 years versus the peak in the financial year 2008-9. This also shows where very recently electricity use was meant to go, or predicted to go, up, up, up. There is now developing a very large gap here between where electricity demand is and where people thought it should be. They used to say electricity demand always goes up. It goes up with the growing economy. But no one is saying that No one is saying that anymore. Energy demand is falling. Sure, there are other factors in here, like solar panels and milder weather and the global financial crisis. But there's also the pink bat scheme and the home energy assessments and compact fluoro and LED lighting and people unplugging their second fridges and people installing blinds and awnings and more efficient appliances and so on and so on. Will energy demand keep going down? Will it level out? Will it go up again someday? This mystery is sending shockwaves through the energy industry at the moment. And it is a secret that not even the thermal imaging camera can reveal. Thank you very much.
Thanks, Tim.
Now for my second tip. That's not to have that stuff laying around.
The university knows about that. Thanks, Tim. That's a really riveting presentation. We're open up for discussion. We've got half an hour, so I'll take questions. 1, 2, 3.
Just a comment on the fans, the roof fans. Using them during the daytime is really terrible because it brings that bit of hot air down all the time. Whereas if you leave it sitting up there, that heats up, it doesn't heat up the room as much. So those fans, you're right, are really good at night time, terrible to use during the daytime.
There is a switch on the side where you can spin them the other way, and they're meant to, instead of bringing the air down, they push it up. And maybe you got 12-foot ceilings or something like that. It'd be of some use, but I don't see a heck of a lot of value in that application you're talking about. But I'm very interested to hear from other folks in the room about these sorts of issues. If anybody wants to talk about ceiling fans?
There are very efficient ceiling fans now operated on DC instead of the old-fashioned watt burner.
Exactly. I think we saw some at 5 watts. So that's why I put in my speech here, old ceiling fans. Yeah, there are some very interesting ones that are available now. Fairly expensive still, I believe, but operating on 5 watts could be quite remarkable.
Another question? Sorry?
Don't be too hard on fans, good fans. They work well in a properly insulated house and they're designed to work together. But I'm interested in the camera. I've seen some that are getting down in price, even less than $1,000. And I was even thinking of buying one for myself. Are those cheap ones really too crappy, like the small field of view and stuff, or are they effective and able to be used?
Yeah, I've never used one, so I don't know. So I can't answer that. I don't know if anybody else has experience with infrared cameras to help to answer that question.
Where can I get one in the city of Yarra? Like a library or something?
They're ideal items to be purchased by groups, aren't they? Be given out to members or something. The ATA, for example, they purchase one. Alternative Technology Association.
There's the Yarra Energy Foundation.
Bayside Council has one for their residents.
Charlotte has one.
And who was it? Peter?
Yeah.
You were mentioning you've got a laser. Was it a laser thermometer?
The laser thing that determines temperature, but you spend a whole day trying to measure stuff. So it has its application on, say, the hot water service possibly. But that is pretty exciting, and I want to get one.
But I would encourage folks to use your fingers, because you can detect these differences. And you go around the wall and it's like, whoa, what's that? Pick a hot day, when the sun is beating on the spot that you're interested in, and you'll be able to tell. In a lot of cases, you're going to get up on the ceiling and feel the difference between the wall and the ceiling. So that's possible.
Another question?
I've got two questions. One is, can you comment about underfloor insulation? And the other thing is that you've missed out in your presentation a really extreme heat source, which some of your suggestions would avoid, and that is bushfires. Awnings and cladding on the windows can save your house from bushfires. If you add that in, that will add additional Australian effect.
Yeah. I'm only going to add stuff that I'm comfortable with. I've never lived out in the country in the bushfire areas. It scares the heck out of me, so I probably never will. But we're lucky to have Trent, who is our project director on the buildings plan, to answer that underfloor insulation question.
Well, we're certainly proposing underfloor insulation, and we've been doing a bit of research on spray foam insulation the last few weeks, and certainly that's an option. Closed cell spray foam just under the floor, but also there's a company called EcoMaster that will install underfloor insulation, suspended timber floors. They usually just put some bats and then roll out air cell, just reflective foil insulation, and that covers it.
What sort of savings does that provide?
I'm not sure the percentages, Richard. Maybe you have some numbers up, but yeah,
The underfloor will lose about 15% of the heat from the room. The ceiling will lose about 18%, 18 to 21. So it's almost the same as what the industry.
there's also a lot of air gaps. I've stayed at people's places in Brisbane, and it's great in summer to have all these sort of air gaps and airflow to cool it down in the evening, but in winter it makes it terrible. So actually sealing the air gaps is another major factor in reducing heat loss.
And certainly I didn't have any photos of floors tonight, but yeah, certainly we have looked at some floors, and for a house that is well insulated in the ceilings and the walls and has good treatments on the windows, definitely the camera says look at the floor, because you'll find the floor might be at 13 degrees or something. So it does raise the idea that if you've done all those other things, then digging around under the floorboards is the next thing to do while you're pulling out your ducted heating system.
Tessa?
Yep.
Sorry, the woman.
Me?
Yep.
Oh, sorry, Robert.
Oh, sorry, Robin.
Just the ceiling thing, one of the concepts is that, it circulates the heat. So instead of you heat a room, all the heat going up, moves it around.
Yep.
Sorry, there was another one.
Yeah. I just wondered, Tim, if you had any studies on the effect of carpets or rugs on the floor before heat loss.
Yeah.
What effect that had.
Yeah, every little bit's going to help, as we all know from walking on a floor versus a carpet. Even feels better, but it would be reducing the heat coming through. I know one thing that we did in our renovation. We have a 100-and-some-year-old weatherboard house, and so we were doing a renovation, and the floors up the front, they were just going to be, there's these boards, and there are gaps and everything else through them. And I discussed some things with the builder, and he really couldn't figure out what I was on about. So in the end, myself, I ended up putting down 4 millimeters of either a plywood or a composite wood, put in about 1 million nails. I put glue under that before, glued it down, nailed it down. So now I know, there's an extra 4 millimeters of that. So I've definitely stopped the air gaps, and it's a little bit more insulation. Getting under our floor is very difficult because it's so low. So that was one thing we did. Then the carpets. So that was one thing, mostly just to keep the air gaps out. And so I was there on the weekend. I put down 22 sheets of this plywood, nailed it down without it. The next day the builder came by to finish a small part of the renovation, and he brought his nail gun. And I said, gee, could have used you yesterday.
Carpet usually has about insulation.
Sorry, not you, the guy in Cheshire.
The issue with fans, there's a thing called psychometric charts which show you that, I can't remember what the numbers are, but you've got air movement.
in a room, then you feel several degrees cooler than it actually is. So you can live at 24 and feel like it's in the 22 degrees. So there's a lot of fun having a fan.
Definitely all for small fans. Definitely. Because in the ceiling fan we saw there, that's an extra 200 watts of heat going right into the room.
Big changes here in new houses around my place, East Kew. There are 2 houses built recently with huge polystyrene blocks, actually hollow blocks, solid on the top, but hollow honeycomb underneath. Incorporated in the slab.
Yep.
Any results on that sort of thing?
We actually visited some friends that had that done, so I'm not going to be able to give you a quantitative answer. But certainly they were saying that had a lot better thermal properties than your ordinary slab, and particularly for cool climates where I think that's right. Yeah, I think they're recommended for cool climates. But the other thing that he was saying is that it actually seemed to be cheaper because you're using the polystyrene or whatever rather than extra concrete. So he was saying it was actually cheaper, and in that case, it would become the standard pretty quickly if it were cheaper.
Yeah, I think with concrete slabs, perimeter insulation is a good option because you get most of the heat losses around the perimeter rather than through the underneath, because that's where you get, it's not just the soil, but it's also air, and you're getting much greater heat transfer. So there's something. I mean, that's something we haven't put in the buildings plan because it's sort of the next step later is to deal with that sort of thing.
But you could well see that becoming the standard for new build if it's cheaper, that's for sure.
It is a lot.
Sorry,
Okay, well, I've always heard that the air conditioning units are fairly inefficient. Is that mainly the older ones, or are they a lot more efficient now?
Yeah.
And also, how does that compare to other forms like hydronics and things like that?
Maybe some other folks to help me with that one. Definitely the older air conditioners were very inefficient. There is this thing called the coefficient of performance, and these days you can get a air conditioner with a coefficient of performance of 5, whereas back then maybe it was 2, 1.8. I don't know if you look at some of those really old ones. And so the mathematics there, that's a hell of a difference. That's what you see there. And there was another part of that question.
Just to explain the coefficient of performance.
Go ahead, Robin.
2 kilowatts of heat out for every kilowatt of the unit. That's 2 kilowatt.
Right.
And 6 kilowatts of heat, effective heat out for 1 kilowatt going in.
Yep. Yeah, so it's the ability. Yeah, the coefficient of performance is talking about the ability of the heat pump to steal the free heat. And if it's got an inefficient compressor that's using a hell of a lot of electricity run, and it's not very able to grab the free heat, well, then you're going to have a poor ratio of that coefficient of performance. But if you buy the new units, but they efficient all the way around, it doesn't take up a lot of electricity to run the compressors, and they're able to efficiently steal a lot of the free heat, and that's where you get these factors of 5 happening. But I think there's another part of the question.
Yeah, so for instance, we have hydronic heat.
Oh, hydronic and all that, yeah.
And you compared it to gas heat. How does it compare to hydronic?
Oh, well, hydronic's probably being driven by gas.
Yeah.
Yep.
But it's mainly water going around.
That's right. Yeah, and so you saw what ducks could be doing. I mean, in the average Australian home with those ducks under the floor, we got dogs, we got possums, we got kids, we got everything going down there. We got faulty installation to start with. Rats. So even when we had an option years and years ago about heating, the hydronic was seen as better, but it was more expensive. So a lot of folks go with the ducted heating.
And there's nothing stopping you having a heat pump hydronic system.
Bingo.
And there are companies that will install them. So
yeah.
It's just a method of it's just a form of heating. It's not.
Yeah, you've got your method of generating your heat or stealing it in the case of the heat pump, and then you just have the way it's delivered, whether it's by air blowing around the place or by radiation from radiators that you have with the hydronic system.
I lost track of who was putting up hands.
Just as a comment, you can also have solar boost on your hydronic heaters.
Certainly.
One point with ceiling fans. My daughter's 3-year-old unit, the light is built into the ceiling fan in a couple of rooms, and when I had a close look, that was a 100-watt halogen globe
and I did manage to replace it with an identical sized thing that fitted 2 compact fluoros, which gave much better light.
Yep.
But that's 3 years. It's also the whole place is full of downlights, which I had a word at. But yeah, so that was a direct replacement, so I went down from 130 and got a better light out of it.
Yep.
But I have another question for everyone. Has anyone managed to successfully insulate a roller door for a garage? Because the same unit has a west-facing roller door, but the garage is turned into a sewing room, and it is. I'd love to see your camera on it. But you can't touch it.
I don't know. We might get a German warning message on that. It might be too hot. I don't know.
The easiest way to fix that is an outside light.
That's the first thought we've got. But
that'll keep
that will all go
hot.
That's number one.
Yep. Keep the heat outside. Yep.
I'm thinking maybe in winter, does anyone manage to actually somehow insulate just a standard garage roller door? Well, that's what I'm thinking of. So
there is core roof paint, and so you could actually apply coating to the door, which normal core roof paint might just work really well in summer, in sort of reflecting and it both works on a reflective and an emissivity basis, so it rejects and reflects as much heat as possible. And there has been some, the name escapes me, but there is a type of core roof paint that Melbourne Uni's been doing some research on, which is showing it's actually got insulating properties in winter, sort of ceramic particles in it as well. And it's to do with the emissivity effects, but it actually is able to help reject the sort of internal long wave radiation. So it's a possible option there. Core roof paint is something we've considered for the buildings plan. It's certainly worthwhile.
Hang a forward curtain or a cosmic master.
Oh yeah, well it's not my place, and I have to sort of.
Just ideal.
I've got to push them in to have the reception.
Just because everyone's chucking their hands up at once. If someone's going to talk, does someone want to answer that question? Or if so, just put your hand up.
Well, one thing that's probably more of a problem is the air gaps in between the doors and on the bottom of the door. That'll be one of the major things, especially in winter where you get a lot of airflow through these.
You had a point?
Same point.
Okay.
They link like stairs.
Right. So the guy down the front, sorry. No, not you. You.
Can we run the tape back a few metres to the concrete slab? Those foam blocks on the ground are formwork. And before the foam blocks, you had to form the dirt up like that to form the slab thickness and then the thickening beams. But the foam blocks are actually working against you because they're insulating the floor away from using the dirt underneath as thermal mass. As you mentioned, the perimeter insulation is what you're really looking for.
Yeah, that's what I'm thinking. There's, and I can't recall if it's a cool climate versus warm climate, that it's better than the other, depending on what sort of connection you're trying to get in, with the earth. What's that?
When we jump now to the timber floor, you hardly mentioned how much ventilation there was flowing underneath the floor. And many places have got great gaps between the baseboards. The building code requires 6,000 millimetres per square millimetres per metre, which equates to a 6 millimetre gap all the way around. Now, if you're spraying the underneath...
Oh, that's for expansion of the wood? Is that what you're talking about? Why does the building code specify a gap?
Ventilation. And your spraying of the underneath side of the floor worries me because of the breathing of the timber.
Anybody got any comments on this question, this issue?
Well, can I raise a question on these honeycomb floors? Because there are a number of problems that people have experienced. It's new technology, it is cheaper, it avoids doing trenches, which have a real problem because they fill up with water and it rains and all sorts of problems like that. But the strength of the structure is not necessarily that good, and the minimum thickness of cement called up is 85 millimetres, but in fact in many cases people don't achieve that or don't achieve it uniformly, so the strength of the structure is poor. Also there are problems with water movement underneath and the reactive soils, and if you've got a driveway adjacent, there's movement pressures in. There are a whole lot of issues. I'm not sure what the term is. It's not a honeycomb floor. There's some
waffle pod.
Go on the web. There's a whole lot of people that have individual problems, and they really require, serious design by engineers and soil experts and drainage to make sure that you get a good result.
Excellent feedback from a waffle pod customer. Properly designed, they're really good solution to sit above a reactive soil base.
Yeah.
Solve a lot of problems if you just do it properly.
Yeah, if you do it properly too. If it's being done simply to save money,
so it sounds like the knowledge is there. It's making sure it gets applied, which is the same way with insulating a wall. We know how to do it. It's just it doesn't always get applied.
This sounds like 99% of buildings out there are built by people that don't give a shit about the quality of. They're built by contractors to do a job.
I've got some friends that are builders.
Well, that's what they tell me. My friends who are builders, they go on sites and just go, amazing. People have good security lines,
And because the purchasers of these buildings have no idea. And no way we can look at the thermal camera. There's no way we can look at these things to know whether it's done right.
Yeah, and I suppose that's the point I do want to make. I didn't have time in my proper speech. But yeah, this ought to become part of the regular process of buying a home, selling a home, building a home, renovating a home. Because when they first decided they'd insulate Australian homes, it was a fine thing to say, we'll insulate it, and there'll be a standard. But who's checking? How do you enforce it, just like anything else? Because like I said, in the snow country, the snow enforces it. Because you'll know in the first winter, you'll have ice on the inside of your wall, or you'll have condensation or something, and then you ring up the builder and he comes back and fixes it, and then he does that twice, and then finally decides to do it properly every time from now on. But in Australia, there's not really any check that the climate's going to give you. So I think it is going to take something like this to be brought into the play.
And builders have been getting away with it for years. What do they care about a house 15 years down the track?
Or even, it could be the next season. It's just, it could be the next season, but the homeowner doesn't even notice how bad it is compared to what's possible. I'll let Trent try and get control of this group again.
There's a question in the back. Someone's been had their hand up for ages.
I'm just wondering if you might be able to talk a bit about, in a sense, what might call the downstream effects of doing this in 30 odd houses. I'm just wondering if you've got any sense of what that's actually meant in terms of energy use within the dwellings, and I guess some of the issues that the households might have faced in trying to come to grips with often some quite difficult issues, insulation of the existing walls and such like. So, is there anything that you've picked up about the downstream effects?
The second part of your question there about the homeowner, certainly there's a bit of bedside manner and that sort of thing, an interpersonal relationship when you go in to do a thermal assessment. And I generally come in and say, okay, it's going to be like a trip to the doctor. It ain't necessarily all going to be good news. You'll find some things that are good, some things that are bad, some things you fix, some things you can't fix, some things you don't want to fix. And so you do get in a bit of that psychology a bit, and you just reinforce that you're going to try and leave at the end of the day with just giving them a couple of ideas of things that they can do. And maybe the doctor's the same. Quit smoking and get off the alcohol or whatever. But now the first part of your question I didn't actually understand.
Well, I'm just wondering if the households are reporting back in any ways, what difference it's making to their energy use.
No, I don't. I've not gotten. I was thinking about that question, and I might get that question today. I was thinking about that, and no, at Bayside we haven't had a lot of feedback. Some of the folks that signed up for this, they're not even sure where it's. You explain it to them, but they're not even sure. They don't know if it's a government thing, a council thing, a volunteer thing. So they're pretty confused by who's there. Anyway, I've gotten a lot of feedback on my assessments, like thanks, great job, gave us a lot of good ideas, that sort of stuff. Whether folks have actually done anything, no, I can't report a lot of stories there. But this is one of the things that we can keep an eye on as to where these numbers are going.
There was a question just the striped shirt, with the check shirt. Is it you? Sorry.
Lots of things to throw in on the cost thing. We're all to blame because Australians just buy cheap. We don't care. As a society, we buy the cheapest thing we can get, so that's what the builders are going to do. On the slope question, I think generally it's the slope's working against you in winter, it's bringing the house temperature down. In summer, it's working marginally for you, but generally, if you're designing from scratch, you're better off just having the living space insulated from the slab and just control that environment. But my real question was about, so you've got all these images of hot surfaces in summer. Maybe I should know the answer to this, but is it primarily transmission or conduction and convection that's driving the transfer from those hot surfaces into the room? Because that would affect your easiest way of rectifying the problem, I guess.
Yeah, I suppose as a chemical engineer, I was familiar with radiation, up at 2,000 degrees in a furnace or whatever, but I never really thought about radiation much in our daily lives. More thinking about conduction and convection all the time. Stop a draft, put on a jumper, lean up, etc. But spending a lot of time with this camera, what it does is it does give you infrared eyes. So I'll be saying something to my wife, we're going to cook something in the slow cooker. Let's put that in the garage tonight rather than leaving it in the house all day long. And it's why. And it's like, well, I can see it with infrared eyes, so I know. And that radiation. I was working in my garage today, and the floor was cool, but I could feel the heat. And I'm like, well, why is it so hot? Well, it's that garage door. And if I'd had this thing, it would have been glowing. In the garage, it looked dim and dark and cool. But I could actually sense the radiation. So you spend a lot of time with it. You develop a seventh sense or something? And so I would say that radiation is really important and is what this camera is picking up. So it would be the impact of a lot of the things you see there. By the way, I'll be presenting again at the Alternative Technology Association on the 20th of March. And it's a double header. The other guy's going to talk about that method where you put a fan on your house and suck the pressure down, and that way you can get an idea of how big your leaks are. And that would apply more with your with your convection and everything. And so leaks coming in and cold, drafty parts of the house. This doesn't pick up that well. Some folks said you didn't get good shots of the floor or whatever, and I think it's because that's more operating on the convection, which it doesn't really have too much of an impact on the floor as it comes through, so I don't get a good photo, but you can feel it because it's a cold draft blowing on it. So this thing doesn't pick up cold drafts that well, and there's other issues. Good question.
A few people put their hands up who've already spoken, but is there anyone who hasn't spoken and wants to speak? You had a question for me?
Yeah. Just a question about the working fluid inside the aircon. I believe it's not environmentally wonderful, the chemical inside it. I had an aircon installed recently, and there was a mob around Melbourne, I think just one mob who deals in an environmentally friendly working fluid inside the air conditioner. And they said it had better COP as well, better coefficient of performance. Is that something you address or something you have a comment about?
Well, in the old days, of course, you had your ozone-destroying chemicals in the refrigerant systems. And, we don't just have to harp on air conditioners. In houses, there's air conditioners, there's cars, there's fridges, all these things use these fluids. So these fluids are all over the place, and we need to keep them under control. In the old day, they were very, very bad, not only from an ozone-destroying point of view, but also from a greenhouse global warming potential point of view. These days, there are fluids that they use that are better, but I think they're still meant to do a good job of keeping track of them and recovering them because they still would have an impact, I believe.
So there are some ones now that are quite environmentally neutral.
If they're hydrofluorocarbon based, they're generally not good. So because we went from R22 to R410A, and R22 had an ozone depletion potential which was not good, so we dealt with that. But the R410A has a fairly high global warming potential, and if you take a 20-year horizon, it might be 6,000. So one molecule of R410A will equal 6,000 molecules of CO2 in the atmosphere, which is pretty huge. So you don't really want much leakage. We did do a bit of research about it, and so with things like fridges and hot water heat pumps, certainly, for hot water heat pumps, CO2 is a pretty good option. It's actually more efficient because it's a different cycle. It's called transcritical cycle, and refrigerators, there's green freeze, which is R600 isobutane. And that's most Electrolux fridges, and I think they've got another, I think it was Westinghouse associated. There's two brands rolling out isobutane, or you can buy them, and they're global warming potential of 3, so that's a big saving from several thousand. And the problem with air conditioners is that there isn't actually, propane's a really great alternative that should be used, and in China there's been European programs that have funded the conversion of factory lines to propane-based air conditioners, but the main problem is that the rest of the world, was driven by the air conditioning industry to take on R410A, and they don't want to go down the propane road. And companies like Daikin and others who manufacture hydrofluorocarbons really are campaigning strongly against going down the propane road. So if you know any air conditioning sellers who sell a non-hydrofluorocarbon based refrigerant, come and talk to me afterwards.
Yeah, good. Yeah. There's a lot in Melbourne who do it, and I think they should be getting huge amount of publicity.
There is one company called Solarpool.
No, it's one lady.
Hang on a sec, Matt.
Just the question on the spray foam before I missed the concern. Talk about the 6 mil gap and that being bad to close off. What was the actual concern, and was there an answer to it? There was a lot of stuff going on at the time.
So that was the question from down here, and the 6 mil gap and the foam might degrade your wood.
It's a requirement of the building code that you have ventilation underneath the timber floor, and the ventilation is equivalent to a 6 millimetre gap all the way around.
Well, that's under the floor, not into the house.
Oh no, this is subfloor.
Is it ventilation or is it to allow expansion of the timber?
No ventilation.
That's the other dimension, yeah, it's not like that. It's
Underfloor is
something.
supposed to be dry, and to keep them dry, you need ventilation.
So it's under the floor, it's not coming into the house.
Oh, okay. So you just the spray foam is just underneath the surface of the floor.
So moisture would have to get through the spray foam to damage the wood.
Or from inside out, inside.
Okay.
Yeah. But the spray foam is on the timber?
Yes.
That's what worries me.
Can't timber breathe up into the house?
Yes.
But they're using the spray foam.
Not necessarily.
It's sealed.
Yeah, the closed cell foam is different. Yeah, the closed cell foam provides a sort of hard surface seal.
Yes, that's the problem.
There's a big problem with mildew.
Yeah, we've certainly
mildew or dry rot,
yeah.
and that'll destroy your house faster than lightning.
We've been very thorough. Matt has done a lot. We've been doing a lot of thorough work looking at insulation options to avoid condensation problems. So, but yeah, as someone was mentioning, that there's a lot of that it's quite common in the US. The flake, and it's probably the most common way of insulating subfloor houses in the US is to use spray foam. So, yeah, Matt, did you want to add anything or?
No, I was just curious about what the just moisture.
Right, now people with questions. You had a question, Jim?
Yeah, just going back to refrigerants for a moment. Wasn't there I recall reading somewhere there was a safety concern about using CO2 as a refrigerant for domestic air conditioning, just because you've got CO2 under high pressure that could leak out into rooms and stuff like that. Does that come across? Does that come out of what?
Basically, we're not with CO2 because you might only have 100 grams of charge. I mean, you don't normally get air conditioners that are CO2 based. It's to do. I'm not going to go into the reason why, but the heat pump hot water systems. Japan for years have had CO2 based heat pumps. They're called EcoCutes, and they're far more efficient than whatever else is on the market. You can buy products in Australia. Sandon sells a CO2 heat pump. And they're all totally, by Australian standards, fine to sell. Propane is flammable, so there is problems. The standard limits the size of the charge if it's a flammable refrigerant, but it's.
I have propane in my car, air conditioner. That was permissible at the time, and I think it is now because of the work done by the air conditioning supplier. Yes, but in Germany, every car has propane. They did lots of testing, like we always get into the car, and it doesn't get up to an explosive level. So it's a brilliant bit of marketing by the suppliers of the company.
It's 8 o'clock, so if